Hello, this is a chemistry video on acid-base reactions, and we are following Brown, LeMay, Burston, and Murphy's Chemistry, the Central Science. We are in chapter 4, which is on aqueous reactions, reactions in solutions. The previous video was on precipitation reactions, where all of a sudden, poof, something comes out of the solution. Where did that come from? But this one is on acid-base reactions. All right, some definitions. Now, you may have encountered acids in your life, hopefully not too close. Orange juice is acidic. It has that kind of sour taste to our. We have a taste bud that acid alert. Sometimes you can get a little acidic in your stomach, and you need a little bit Pepto-Bismol, which is a base. Bases and acids neutralize each other. We'll talk about that in a second. And so you may have some reaction with acids. Acids can be used in cleaning. They eat stuff up. But technically speaking, an acid is a substance that becomes an ion in solution, yielding a hydrogen ion. So what is a hydrogen ion? Well, hydrogen is one proton and one electron. And so if it becomes an ion and loses its electron, it becomes a proton. And so basically, more technical definition of an acid is it's a proton donor. It gives a proton, which is the same as a hydrogen ion. So an acid is something that's a proton donor. You might think of sulfuric acid has hydrogen, that it donates. You might think of hydrochloric acid, which we have some of that in our stomachs, donates a hydrogen. So that's the chemistry behind an acid. It's a hydrogen giver. I want to give my hydrogens away. That's an acid. A base, on the other hand, gimme. A base is a proton receiver. Open up the doors, let in the proton. And so when a base takes a proton, it forms this hydroxide ion, OH -1 ion. And so we think of like sodium hydroxide would be a base with NaOH and the OH part. That's a base. All right. It's all about that base, All right. So this is some definitions. So let's talk about acids a little bit more. Acids can be either monoprotic or diprotic. Mono means one, di means two. And so here are some monoprotic acids. Hydrochloric acid, HCl, has one hydrogen. Hydrobromic acid has one bromine. Hydroiodic acid has one hydrogen. I'm sorry, did I say one bromine? I meant one hydrogen. Nitric acid has one hydrogen. This is chloric acid, I believe, has one hydrogen. And this is perchloric acid, has one hydrogen. So these are all monoprotic acids. These are all strong acids. H2SO4, I mentioned, this is sulfuric acid. This is diprotic. It's to die for, but please don't. It has two hydrogens. So again, as I said, a acid tastes sour, like the citric acid in orange juice or something like that. And of course, if it gets more acidic, it tastes more sour. All of these above here are strong acids, which means they're strong electrolytes. An electrolyte is basically an ion in solution. It's a charged thing in solution. So acids, ladies and gentlemen, acids. Now, any ionic compound will also be a strong electrolyte, by the way, because what is an electrolyte? It's charged particles in a solution. What do ionic compounds do? They become charged particle or things in solution. So, okay, acids. What about bases? Bases taste bitter. Now, my parents never put soap in my mouth. I had good parents. They would not do something like that. But soap would be an example of something that is basic in the chemical sense. Pepto-Bismol would be basic. Magnesium, the kind of, what do you call it? Hold on a second. Milk of magnesia, that's what I was going for, is basic. Those, and why does Pepto-Bismol help your stomach? Why does milk of magnesia help your stomach? It's because they're basic. And what's causing your stomach to hurt is acid, too much acid. And so you take a base that isn't harmful, and it neutralizes the acid somewhat. By the way, I thought this was interesting, and I might as well say it too. This is a footnote in the chapter. The footnote says, that we've tasted a lot of acids in our life, but it makes sure it has a little note here. Tasting chemicals is not good practice. Okay, just in case you were thinking, tasting chemicals not gonna do it. Okay, stay away from tasting chemicals. Food, fine, but stay away from the chemicals. So strong bases includes, for example, metal hydroxides, the OHs. So this is from 1A, which is the very first column in the periodic table: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, or cesium hydroxide. I didn't even know you could get these. I mean, anyway, but they are strong hydroxides. And then 2A, this is the second column: calcium hydroxide, strontium hydroxide, barium hydroxide. These are all also strong bases. What's the common feature in all these? Hydroxide. Ammonium, by the way, is a weak base. NH3 is a weak base. All right. So neutralization reactions. I have a titration thing behind me. Titration is where you basically drip, drip, drip the opposite of whatever. So if you're trying to neutralize an acid, you drip a base. If you're trying to neutralize a base, you drip an acid. And usually you have some sort of an indicator in the solution that changes colors. So phenolphthalein is one that I remember in college that we used, or maybe high school, to neutralize things. But there are others basically the solution, when it goes clear, for example, that might indicate that your reaction has been neutralized. So bromethymol, for example, is blue when it's basic, and it's yellow when it's acidic. So if you had an acid with some bromethymol in it, it would be yellow, and then you just drip, drip, drip until it goes clear, and then you know we have neutralized the acid. Or if it was blue and basic, and you drip, drip, drip acid into it, when it turns clear, we have neutralized the base. So neutralization reactions basically combine an acid and a base together, producing a salt and water. So if we take this most basic of neutralization reactions: hydrochloric acid in solution, aqueous, sodium hydroxide in solution. If you drip, drip, drip these until they're equal, then we end up with water, because the hydrogen pairs up with the hydroxide. HOH is H2O. And then the sodium, the chloride, they basically stay as ions, but they get together in solution. Sodium, well, actually they don't. I'm sorry, I've made a mistake here. One moment. No, I haven't made a mistake. Sorry. This isn't going to come out of solution, but it is a salt. The water is going to bond in a molecular kind of way. The sodium chloride will remain ionized in solution. What was I thinking? I should have never doubted myself. I'm always right, except when I'm not. Okay, so here's a nice little neutralization reaction. It's also a metathesis exchange reaction too, because swinging your partner, they trade partners, right? So it's an exchange reaction too. But that's a neutralization reaction where you take an acid and a base and you combine them and you get water and a salt. Now, although acid plus base equals water and a salt. Now, sodium chloride actually is the salt that we are all well acquainted with. But there are other things that in chemistry are called salts. Potassium chloride would be called a salt as well. In chemistry, a salt is any ionic compound whose cation comes from a base. Cation. Cation. Cats are positive. Yes, so sodium is the cation. And anion comes from an acid. So chlorine is the anion here. And so sodium chloride. So a salt is any ionic compound whose cation comes from a base and anion comes from an acid. Okay, so now you know the technical definition of a salt. It's not just sodium chloride. And I don't mean a salt. I mean a salt. Okay. You've ever heard of a litmus test? You know, we're not going to hire you unless you pass our litmus test. It comes from chemistry. Litmus is for example, litmus paper. You stick it in an acid, it turns red. You stick litmus paper in a base, it turns blue. And so the litmus test can tell you whether something is acidic or basic. And I've already mentioned bromethymol blue as something that turns blue in a base and yellow in an acid. All right, and I also mentioned phenolphthalein as another indicator of these sorts of things. Okay, let's finish this with acid-base yielding gas reactions. Let me get my unfolder working here. All right, now that's better. So here's a acid-base reaction, an exchange reaction. So we start off with 2 hydrochloric acids and sodium sulfide, and they're both in solution. And what's going to happen is the hydrogen is going to pair up with the sulfide, and we're going to get hydrogen sulfide gas. And then the sodium and the chloride are going to pair up, and we're going to get a salt. Here is an acid-base reaction, acid-base. This is serving as a base. It's not a hydroxide base, but basically, and it's going to result in a salt and this gas. Now, by the way, hydrogen sulfide gas is the smell that the sulfur smell in farts. I just thought you would want to know. This is not the precise fart equation because you do not want to be ingesting sodium sulfide. I just don't do it. But hydrogen sulfide is, I think 1% of a fart is hydrogen sulfide when it smells like eggs. All right, I just thought you'd want to know. But so here we have an exchange reaction, swing your partner, they trade places, and we end up with a gas and a salt. There are also carbonates and bicarbonates mixed together, give off carbon dioxide gas. So here's an example of that. So hydrochloric acid plus sodium bicarbonate. I don't know why they call it bicarbonate because there aren't 2 carbonates here. You have a hydrogen and a carbonate. Sodium carbonate is basically similar without the hydrogen. This is sodium bicarbonate. And let me sodium. I want to get the equation of sodium carbonate. Sodium carbonate has 2 sodiums with the CO3 without the H. So this is sodium bicarbonate. And if you take hydrochloric acid and you mix it with sodium bicarbonate, in the end, it takes a second to get there, but the end result of the process is usually sodium chloride, which is a salt. There's my salt from the sodium and the chloride, and then water, H2 from the O, taking away one of the O's, and then carbon dioxide. So this will bubble. If you mix these together, you get bubbles, which yield carbon dioxide. There is an intermediate step here where carbonic acid is formed, which is H2CO3, but carbonic acid is unstable, and so it will push on through eventually to carbon dioxide most of the time. So there you have a nice little. These are some instances where something that is acidic and something is basic come together and yield a salt and some sort of a gas. In this case, a sulfide gas, and in this side, a carbon dioxide gas. Well, this has been acid-base reactions in our chapter on aqueous reactions.